Hello everyone, welcome back to another tutorial of data analysis in my channel. As some of my viewers asked me to do a video on cluster analysis, I decided to share the complete procedure of cluster analysis, including how to find exact number of clusters and figure out their inter and intracluster distances. The important thing about cluster analysis is it is highly subjective and there is no only such specific thing we have to do. We do have different types of clustering algorithms such as k-means, density-based clustering, connectivity or hierarchical clustering. In this video, I am just going to give a brief introduction and jump into coding part which is so much productive for us. So, personally I guarantee you at the end of this video you will be capable enough to solve the problem. So don't forget to subscribe if it works for you. So first watch the video completely because the code is continuous. If you miss a line then you may run into trouble, but I will do my best to minimize that. Basically, clustering is nothing but grouping the individual based on different values. I am considering here 15 different maze genotypes with 3 observations. The first one is plant height, whether tall or dwarf. And the next one is disease resistance, whether the plant is resistant or susceptible to disease. And the last one is plant yield, whether it is an high yielder or low yielder. We can group the genotypes into 2 clusters like this, one containing only tall plants and the other cluster containing only dwarf plants. Also, we can cluster these genotypes into 3 groups like this. The first cluster containing tall and low yielding genotypes, and the next cluster containing tall and high yielding genotypes, and the third cluster containing dwarf genotypes, whether they are low yielder or high yielder. So, like this, we can do clustering in all possible combinations. This is how the subjective nature of cluster analysis starts. So, let me tell you the best possible way of solving this problem in the coding part. So let me start with the structure of the data frame. In simple terms, how should we have to enter our data in an Excel file? This is the mean data of different P genotypes. If you don't have any replication, then your data is good to go. In case you have replication, then you have to take the average values from replicated entries and keep the mean data only. Simply, the number of rows is equals to number of unique genotypes in the study. After entering the data, you have to ensure that it is saved before importing into R. So it control as or command as whatsoever for you. So let's open the R Studio. If you are not familiar with R Studio, such as how to install it in your PC, how to install and load a package, etc., there are lot many videos in the YouTube. You can check in. I don't want to waste your time. I just get directly into the coding part. If you are interested in theoretical part much more, I just give some of the links in the description below. You can check it from there. First, let's bring the dataset into the environment. From this tab, we have to select from Excel and we have to browse where the dataset has been stored. And I have stored my dataset in desktop, so let me select that. If your data is stored in a different sheet, we can select the sheet from here. So in default, the sheet will be first. Then we have to ensure that all the variables are in doubles, that means numbers. After that, if we are interested to change the name of the data frame, and we can do that from here, and then we have to import. Then we can check the structure of the data frame from here. Then let me select a new script for writing the code for our data analysis. If the text is not visible, please increase the resolution of the video. And after each and every argument, we have to mention comma. And after each and every line of code to execute, we have to press Ctrl and Enter. Let us start keeping all these things in our mind. The first thing we have to do is scaling the data. In simple terms, removing the units of the variables in order to reduce the probability of a single variable dominating the entire cluster analysis. Suppose you have plot yield in quintals per hectare and plant yield in gram per plant. If you won't scale, then the plot yield will definitely dominate easily over the plant yield and we can't be able to give enough justice for our clustering. So we will store our scale data in p.s. While doing scaling, it is only possible to scale the data of a quantitative variable. So here we can see in our dataset the serial number and genotypes are not needed. So we have to remove serial number and genotypes. So let's get into the code and remove that here. Inside the scale function, type the name of the data frame P, and in order to select what we need, we have to use big brackets. Inside them, we have to code for rows and columns like this. Since we want all the rows, leave the first value empty, put comma. To remove first two columns, type -1 to -2. Here these two tells us it is from 1 to 2. Execute the above line of code, and in order to check the scale dataset, type p.s. This is how the scale dataset looks like. So after scaling, the next step is to get a dissimilarity matrix, which includes the Euclidean distance between the points. If you want different metrics other than Euclidean, such as Manhattan or binary, you can change it by selecting the different method in the distance function. So just type $dist to know what are the different distances we can use. So let me store the dissimilarity matrix in D. The function used here is dist. Inside that we have to mention the name of the scale data frame p.s. So execute this line of code, Ctrl plus enter. Before taking a look into the dissimilarity matrix, we need to increase the maximum lines which has to be printed. So in options, change the max.print to a maximum level. So type D and then execute, Ctrl plus enter. So in the console we can see the appearing of dissimilarity matrix. Wait until the red beep stops. The first algorithm I am going to use here is k-means. If you already set your mind to fit the individual into exact number of clusters, suppose 2, we can directly do that by setting the k with the number of clusters equals to 2. To do that, type k2, use k-means function. Inside that, just mention the scaled dataset p.s and the number of clusters we want, that is 2. In order to inspect the clustering, type k2 where the cluster has been stored, and in order to find the cluster membership in k2, select clusters. In majority of the times, we need to know what are the optimum number of clusters. There are many methods to find optimum number of clusters. Among them, the most often method is elbow method using WSS plot function. If we do it for an ideal dataset or a dataset which is clean and tuned, such as Iris dataset, you will find the king carbon in the plot very much easily like this. In this, anyone can find the optimum number of clusters very much easily. But this is only expectation. Let me show you the reality. In order to keep it simple, I plot the graph using fviz NbClust function which is present in the package factoextra. So install the package factoextra. You can type the command like this, install.packages, and within inverted commas we have to mention the package name, that is factoextra. Then Ctrl plus enter to execute this line of code. So wait until the red beep stops for the first time while installing a new package. And you can also install a new package by selecting packages tab and clicking on install. So click on install. There you can type the name of the package factoextra and then select and click on install. There is no need for me to do this because I have already given in the command. Factoextra also requires ggplot package in order to function. So let me load it. Because I already installed, there is no need for me to install it once again. And then load the factoextra package into the console. Inside the library function, mention the package without inverted commas in order to load into the console. After that, use fviz NbClust function. In that, we have to select the data p.s and type of clustering, here k-means clustering, and the method WSS within inverted commas. So wait until the code executes, until the red beep stops. So this is the reality. What we often came across, we can't find exact number of clusters just by looking into the plot. So there is another method called silhouette. So we can just copy the above line of code and change the method from WSS to silhouette. So be careful while typing the spelling. It should be correct in order to execute. So after the code executes, we can see from this graph that the optimum number of clusters is 2. So close the graph. but I do prefer to find the optimum number of clusters using a package called NbClust, which uses 30 different indices to predict the optimum number of clusters. If you are interested in that, you can check the link given in the description. So install the package NbClust. Be careful, it's capital N, small b, capital C, and rest will be in small. Also load the new package like this. In the package stub, select the package we need to load. So here I want NbClust package, so click on the NbClust package. This is similar to the way we load a new package with the code. Inside the library function, we have to mention the name of the package, that is NbClust. NbClust package has only one function, so we can easily copy the function from the packages. So click on the NbClust package, and from here copy the code and paste it on the console. So let me do that. Copy. After that, just tweak the code a little bit. So for data, we have to select the data frame name, that is p.s, and after that we need to change the method. So here mention k-means within double inverted commas. Execute the above line of code. Wait until the results appear in the console. So in the results, we have to look for the conclusion. In the conclusion, it will show what is the optimum number of clusters. So here, the optimum number of clusters is 5. So set the number of clusters to 5. So in order to do that, let's store the clustering in set k, and within k-means function we have to mention the scale dataset name, that is p.s, and the number of clusters, which is 5. Execute this line of code. In order to see the cluster membership, we have to select the clusters which is stored in set k variable, and we can also find this many things stored in set k variable. So if you want, select anyone and click on that and execute that line of code. We can even see how well the clustering happened by plotting the dataset by setting different colors for different clusters. Since my computer is running in dual core Pentium processor, it takes more time to execute all the graphs, so wait until all the graphs gets executed. Of course, we can't see anything in this plot because of more number of variables in my dataset, but we can export it and then view if it needed. I will talk about exporting graph later for Dendrograms in this video itself. So close this plot. This is all about k-means clustering. So in the next method, I am going to talk about hierarchical clustering. The function which is used for hierarchical clustering is hclust. If you are not familiar with it, then we can look at it by typing $hclust. So here we can see much information about hierarchical clustering. These are the methods we can use in hierarchical clustering. So in this tutorial I am going to use ward minimum variance method with square Euclidean distance, and we are familiar with the NbClust package and the function NbClust which we used in k-means. So we can use this method to find the optimum number of clusters in hierarchical method also. So we can change the method here only, but I decided to copy all the code and paste it over here just for the reference purpose, and we can change the k-means method to ward.d, which uses Euclidean distances, not the squared one. So in order to find squared Euclidean distance, we need to use ward.d2. So from the NbClust function, the results are out. So here we can find the optimum number of clusters for ward minimum variance method using Euclidean distance is 2. So replace the ward.d by ward.d2 in order to find the optimum number of clusters using squared Euclidean distances. So after the results are out, in the conclusion we can find that the number of optimum clusters are 3. So this will be useful in plotting the dendrogram and separating the clusters. So let's store the clustering in ward SC. Within hclust function, we have to mention the distance matrix or the dissimilarity matrix, that is D, which we coded earlier. Then we have to mention the method within the inverted commas. In order to get the dendrogram, just plot ward SC. And the dendrogram what appeared here looks very much awful because of more number of genotypes and two plots getting plotted instead of one. So let me tell you how to correct it. So let's close this chart and getting into the coding part. And the first thing we have to do is plotting the same dendrogram with the numbers hanged. So within plot function mention word sc. After that for hang set the value to -1 and then execute this line of code. And the dendrogram what we get from this is like this, and here we can see all the numbers are in line. Close these charts too. And in order to get rid of plotting two plots, we have to clear all the history. So in the plots tab, we have to click over here and clear all the history. After that, let's plot the dendrogram with the name of genotypes instead of numbers. For that, in plot function, mention the additional argument label and select the genotypes which are stored in original P data frame. Now we will get only one plot, and the dendrogram will be having names of the genotypes instead of numbers. Then I will show you how to plot the dendrogram with three clusters divided by a border. In that case, we need to use rect.hclust function. Inside that, we need to mention the variable in which the clustering has been stored. Here, word is C, and the number of clusters, which is equals to 3, and the border color, we need a border of blue color. So mention blue within double inverted commas. We can select different colors for borders too. So to do that, in the border, just mention the code which represents the color. Here I am going to mention three colors from 2 to 5. So 2 is to 5. Even we can change the color of the lines and labels, but I think this much of makeup is enough for this. So in order to export this graph, click on export and select save as an image. So from this tab, we have to choose the directory or path where it has to be stored. So I will store it on desktop. Then the name of the file, so I will change it to dendrogram. Then I will click on save. So let me open the dendrogram which is saved on desktop. So this won't make any sense because more number of individuals in my dendrogram. So let me tell you how to export with optimum number of resolution. So here by maintaining aspect ratio, we need to increase the width. So it is in pixels. I will multiply the width by 4 times. So 638 or 628 multiplied by 4 times is 2512. So let's change the width. If the aspect ratio is fixed, then the height also changes. So after that, we have to change the name. So I will change to Dendrogram 2 of full resolution. Then I will click on save. So from the desktop, we can look at the second dendrogram. So this dendrogram will be useful for our academic or research purposes. So let's close it. And in order to find the cluster membership, we have to use cut tree function. Let me store the membership in HCM, hierarchical cluster memberships. So inside the cut tree function, we have to mention the variable where the clustering is stored. Here word sc and the number of clusters, which is equals to 3. Then we have to execute this line of code in order to find the list of membership. So type HCM in order to know the list of membership. So here we can find the list of membership of hierarchical clustering. This will be useful for finding inter and intracluster distances. So let's get into that. So the package we need for finding inter and intracluster distances is CLV. We need to install that package. If it is not installed, then go on and install by selecting install.packages command. Within inverted commas, we have to mention CLV. I have this package already installed, so I will load directly from the library. For k-means clustering, we will store the data or the distances in a variable called KID. K means inter or intracluster distances, and the function which is used here is cls.scat.data, which refers to clustering scattered data. So within that function, we have to mention the scale dataset name, that is p.s. Then the membership. For k-means clustering, it is stored in set k. So type set k and in that select clusters and execute this line of code in order to find the distances. In order to take a look at the distances, we need to print it. So within the print function, type kid. From this function, we will get these many kinds of distances. So these are the intra-cluster distances, that is the distance within a cluster. And these are inter-cluster distances, that is the distance between two clusters. For hierarchical clustering, let us store the distances in a variable called HID, which refers to hierarchical intra or intercluster distances. So the same function class.scat.data has been used here. So within that we need to mention the p.s data frame and the cluster membership, that is HCM. Execute this line of code, then print HID. If you have any doubts regarding which type of distances has to be considered, such as whether to consider average or centroid or any other, I will give a link in description. You can look into that for more information. In a single table itself, we can mention both intra and intercluster distances. Here, the intracluster distance of cluster 1. Here, intracluster distance of cluster 2. Here, the intracluster distance of cluster 3. Here are the intracluster distances. At last, we will look at how to find the cluster means or the average scores. In order to do that, we can use the basic function called aggregate. So, within the aggregate function, we have to consider the original P dataset, not the scaled one. Then from that, we have to remove first two columns because we can't do any mathematical operations for serial number and genotypes. Then mention the membership in list. Then the needed value, that is mean. Then execute this line of code and there you go. You will find the mean values of all the variables. So friends, I have shared all the information which I know with you. If you like this video, do hit the like button, and if it is helpful for you in your academics or research, not to forget to subscribe to my channel because I do need your support in order to keep the momentum on. Thank you.